Myself and Bilal will be presenting this together. We both work in Eskom transmission engineering. The first half of the presentation will be presented by Bilal. They'll talk a little bit about our environment and as well as different aspects that are applicable to the topic at hand, which is the electromagnetic forces applied to structures. I'll then hand over to Bilal to start off.
Perfect. Good morning, everyone. Good afternoon, everyone, rather. Thanks for the introduction, Azhar. Again, I'm Bilal, and I'll be taking you through the first portion of this presentation, just basic information that feeds into Azhar's discussion on these forces applied to the structure. Okay, so maybe I can just switch off the video so that it can make it seamless for you as we're discussing it. Okay, Azhar, you can go to the first slide. So in this presentation, we will be discussing three basic concepts. The first one is the substation layout, the types of structures, and the protection devices that are in the substation, which then leads to the discussion of electromagnetic force calculations. And Azhar will then take you through that, as well as squeezing out more structural capacity. Okay, so the first thing I'm going to be taking you through is the substation layout of structures and circuit breakers. The types of structures and the circuit breaker. So I'll discuss why we go into the circuit breakers a bit later in the presentation. So let's start off. So typically we have a substation. So where does the substation fit in this bigger scheme of Eskom? So usually it is between the power generation and the distribution. And distribution has some substations in it as well, or a lot actually, and they feed to the end user. So we are in transmission. Typically we take the power, we step it up from the power station, and then you will notice it comes to the substation. And this substation you see in front of you is Pinatage substation. It's in the Western Cape in Macassar. And this portion that is closest to us is the 400 kV yard. So that's 400 kilovolts that are that's in that yard. And the yard opposite that, towards the back, that's the 132. And this is a rigid bus bar substation. Okay. And we will mainly be discussing flexible bus bar, and we'll get into that a bit later. And this is a typical transmission substation. Now, behind this typical substation, you'll see that's a distribution substation. It's called Firgrove, and it's also in Macassar. So all of them are close by to Macassar. So maybe we can move on. Okay, so this is a single line diagram of the typical substation. So you will notice that we have transformer 1, 2, and 3. That's usually on the high voltage side. So that will either step up the electricity or step the electricity down. And it will then be fed into the opposite side where you see feeder 1, 2, and 3. And that's usually the lower voltage in the substation. So just for the purposes of discussion here, you will see that we have a circuit breaker. That's that circle with like a break in the network. And then those that are connecting the bus bars are usually the isolators. Okay. Those are the isolators there. Okay, so we will be focusing on where faults are created in this system. So I just needed you to understand that you have isolators or disconnectors, circuit breaker, and then transformers. And all of these are connected by the bus bars. So you'll see there's bus bar 1, A and B. That's just split. It's for electrical zoning. And then you'll have bus bar 2 on the top. Okay. If we move on to the next slide, you'll notice that we have the physical look of the station. Usually it's a whole lot of structures called gantries in the substation, and these carry conductors. So this is a flexible conductor or flexible bus bar layout. You'll notice that it's, if we can call it in simple terms, steel wire that connects one structure to the other, and the electricity is transferred through these conductors. Okay, and this is going to be the focus of our discussion today. This is the strung type. The rigid bus bar is very similar setup, except that it does not use gantry structures. Each tube is then carried by its own post-insulator system, as you might see later as we go through the presentation. Okay, so this is the basic structural layout, and you'll notice that the bus bar is the ones that go left to right, and then the power will either go onto the stringer, going upwards out to feeders, or coming from transformers, as I showed you earlier, from the bottom. Okay, and that's typically just one portion of the substation. So this could be the 400 kV or 275 kV side. The 132 kV, because it's much smaller, it's a much more rigid structure, and it doesn't concern as much as this 400 side of things. Okay, so we can move on to the next slide. We'll discuss some faults. So faults, as it says, an error in the system which either cuts off electricity. So in an air insulated system, which is the substation we're discussing right now, where the substation is outdoor and air is used to insulate the three phases of the substation. So this type of system, it has faults. Any type of system has faults. And the critical issue here is the short circuit forces that are created due to this type of faults. And we are trying to maintain the system reliability and safety. And in my part of this presentation, I will be covering the types of faults you get, the location of these faults, the electromagnetic forces, what are they, how are they formed, and then the force components that are created due to these electromagnetic forces. Okay, so if we move on to the types of faults in an AIS substation, you'll notice there are five main types of faults: the short circuit fault, an open circuit fault, insulation fault, some equipment failures, and then finally earth faults. So the short circuit fault, you get three main short circuit faults. It's called a line to line fault. So what happens here, and I will show this to you as we go through the presentation, the two of those three conductors in this three-phase system come into contact or come very close to being in contact. And that is called a line to line fault. Another type is line to ground fault. So when a conductor comes into contact with ground, and ground here doesn't necessarily mean the actual ground. It's in terms of electrical jargon, where an item is earthed and it's isolated from being a conductor. And when a conductor then touches this ground, it creates a fault as well. And finally, in the short circuit faults, you'll get a three-phase fault. So this is, as I showed you, there was three lines in the previous slides. Those three lines depict three phases. And now when all three of these phases get close to each other or come into contact with each other, then this will create that three-phase fault. As you can see, those three lines there. Okay, perfect. So we'll move over to an open circuit fault. This is a very self-explanatory. It's when the circuit opens, and because maybe the conductor breaks and there's a disconnection, then the electricity doesn't transfer anymore. So this is another type of fault. It causes an interruption in the circuit. Then we get insulation failures, and as I'll go down later, I'll show you what an insulator is. That's where either the insulation breaks down and electricity can jump from one conductor onto the earth easily, or between two conductors because of insulation failure. And that's the third type of failure that could occur in our substation. We'll move on to equipment failures, and this is again self-explanatory and straightforward. Is if any of these equipment that you find in a substation, for instance, transformers, circuit breakers, any type of equipment that you might find there, isolators included, you will find that will be an equipment failure. Sorry, Azhar, I think you are 2 slides forward. If you could go back one more, please. One more. Perfect, thanks. And the last type of fault is the earth fault. So here the earth fault is when an unintended connection to the ground occurs. So very similar to the line to ground fault, although this is different in that you get earth switches in the substation or isolators with earth switches in the substation. And if the system is live and they put in an earth onto it, then that's called an earth fault. It's an unintended connection. It shouldn't be there. The earth is there to make the area safe. And when the connection is already broken, if it's not broken and an earth is added, this creates an earth fault. But if you move on to the next slide, you'll see that our main focus for today is the short circuit faults, and specifically the line-to-line or three-phase faults. In my discussions further along the line, you'll see which one is the worst case scenario, and then we will look deeply into that type of fault. And for now, just know that these are the main focuses for our discussion, and it impacts the structures or those gantry structures the worst. The other types of faults can be mitigated using protection systems or the different types of equipment that are in the substation very easily. These two, the line fault and the three-phase fault, can be mitigated. We're looking at mitigating it using equipment as well. However, it does cause effects on the structure, and we need to take that into account when we are designing our structures. Okay, so if we move on to the locations of the fault in the substation, there are various places where these faults might occur. And the first I put in here is the bus bar, and this is where we are going to be concentrating on the bus bar. There are transformer faults that located at the transformer, at the circuit breaker, maybe at the isolators and disconnectors. You can get the faults from the instrument transformers or at that area. Some cables and overhead lines could have faults. And obviously, if the protection or control system malfunctions, you get some faults in that area. And lastly, at the surge arrestor. So the bus bar, that's the lines that I showed you in the single line diagram that connect the transformers from the one side to the feeders on the other side, and it sends out electricity through the system. So this is the central point where multiple circuits are connected, and faults can occur due to insulation failure mainly here, or physical damage. However, if there are switching surges, which I'll discuss as we go down the slide, that affects the bus bar's electromagnetic field quite dramatically, and again, the crux of Azhar's presentation. So a fault can happen at the transformer. That's the second one. Faults in the transformer occur usually due to internal insulation breakdown, or if the windings inside of the transformer short circuits, or if you have cooling system failures, which then reduces the insulation and causes the fault in the transformer. This fault can then promulgate all onto the bus bar and increase the electromagnetic fields there. One of our main causes for those electromagnetic fields increasing is the circuit breakers, and that's why it's one of the main issues that concern us, where a circuit breaker can experience a fault due to mechanical failures, again, insulation failures or contact erosion, but it has a fourth type of fault. It's not actually a fault, it's an operational instance of a circuit breaker when there is a fault. So usually when a fault occurs, the circuit breaker will open so that the system can feel minimal effect, and that causes switching surges, which we will discuss later. And that's why I highlighted circuit breaker in my title for this portion of the presentation. We move on to the fourth type or fourth location for the fault. It's the isolator or disconnectors. And faults can occur here due to mechanical failure and dielectric breakdown. Here again, it's more of a mechanical failure. Isolators are there to create air insulated gaps when we want to open the circuit. So the faults could occur if there is a malfunction or a breakdown in the insulation there as well. Then we move on to instrument transformers. This is transformers that measure current or voltage. And if these lead to error in measurements, they could create faults in the system, like opening the breaker unnecessarily or the isolators unnecessarily. Then we move over to cables and overhead lines. The faults here occur mainly due to insulation damage or physical damage. But however, they, especially in the Highveld area, we have a lot of lightning strikes. So the environmental factor of increased current in the system comes from lightning strikes. However, insulation damage or physical damage is quite significant issue as well. It's not for our discussion. Our discussion will mainly be on the bus bar itself. And again, similar to the instrument transformers, if the protection and control systems malfunction, they could cause faults in the system, unnecessarily opening breakers or isolators, and this will lead to failures and faults unintentionally or incorrectly detected by the system. And lastly, the surge arrestor, this ties up a lot more with cables and overhead lines, lightning strikes. However, switching surges, which the circuit breaker might cause, also affects the surge arrestor. So these are there, as I mentioned earlier, as a protection system. It tries to limit the excessive voltage surges. But obviously, the more these surges happen, the more it degrades, and this degradation over time will cause the surge arrestors to fail, and then we will end up with problems. So that's why, if you go to the next slide, I highlighted the bus bar, and the bus bar is what we're going to be discussing, where the faults or the surges affect the bus bar. Okay, so what are the worst case scenarios for this bus bars? And as I mentioned, the circuit breaker is heavily involved in this, and to a certain extent, the transformer as well. And if you go to the next slide, you'll see that we have three types of surge issues. The first is a high interruption of high current faults, right? In interruption of high current faults, this is where the circuit breaker comes in. The next one, restriking and reignition surges. This is again due to the circuit breaker being operated. And the last one is a load rejection surges. And these usually come from energy stored type of equipment like the transformers or motors. So if you look at the first one, what happens is when a circuit breaker interrupts a high current fault. So for instance, if there's a lightning strike and it gets through the surge arrestor, the circuit breaker would open so it doesn't affect any of the other equipment and damage to the substation. And that is interrupting a high current, okay? And it's called a high current fault because it's not meant to be transferred over the system. And what happens is in the switching, when the circuit breaker opens, it creates a surge, and the current that flows at a high rate of change then increases the magnetic field, resulting in strong EMFs on the bus bar. So we'll get into the basic science of EMFs, and the higher the electricity that flows through it, the higher the bigger the magnetic field, and this causes issues on our structures. Okay, so the restriking and reignition surges, so it's very similar to the first one. However, certain circuit breakers, they open and then they close. The reason they close is that it might have been a fault that it read incorrectly. So it closes to confirm if there is a fault, and when it closes and the fault is still there, it will open again, and that's why it's called restriking or reignition surges. And what happens is this type of surge then pushes up the charge on the conductors and thus increasing the magnetic field. And if it repeats quite often, then the transients induced significantly increases the EMFs, creating severe mechanical and electrical stresses. Okay, on our structures, especially the mechanical forces that are created due to this increase in EMFs. And the last one, the load rejection surges. Like I mentioned, those are usually in transformers. If there's a sudden disconnection of a large inductive load, they can also produce severe switching surges. And these are less likely to occur. The one that happens more often is the restriking or reignition surges and the interruption of high current faults. So as we are going through the enhancement of technology, we try to use restriking and reignition surges more often, or rather circuit breakers which cause this. So it's something that we need to take into account when we are designing our structures for these types of circuit breakers. Okay, if we move over to the next slide, you will see the bus bar again, the single line diagram. And as we go through the slide, I'm just going to highlight to you the sections we will be discussing. If you can just click for me, Azhar, it will highlight the sections. If you could just click, Azhar. Okay, so that's the one bus bar. We'll be discussing on that. And if you click again, you'll see the next bus bar. And this is our focus for today. So what occurs in these two areas due to the switching surges, which I discussed. If we move over to the next slide, again, you will see if we highlight the areas, there's two areas, that's the bus bar, and the next area below that is a bus bar as well. So these are three phases, as you can see, three lines running across each section. So each phase is labeled blue, white, and red, or sometimes blue, yellow, and red. It depends on where we are looking at this in the system. Okay. The next slide, we zoom into the structure. So those three lines that you see there are the conductors. The shaded in area on the one side, you'll see it's insulators, and these are connected between two gantry structures, as you can see here. Okay, and if you move on to the next slide, you'll still see the same thing. However, this is now where the current and the switching surges come in. And as current flows in this instance, I'm showing it flowing from the right to left, you will notice that you have an electromagnetic field that runs across this entire conductor. Each conductor has this, and you will notice that if the current is flowing, in this case, right to left, you can use your right hand rule where you stick your thumb up, stick your thumb out. If you stick your thumb out, that's the direction of current. And then the other four fingers shows the rotation of your magnetic field. Okay, so Azhar, if you just click there, you will see some animation of the magnetic field, and that's the counterclockwise in this scenario. Okay. Let's move on to what happens on the next slide when two conductors are next to each other. So you'll see there are four different sections in the slide. So we'll discuss the first one. And Azhar, if you click through it, it will show some animation. So the electromagnetic fields, if two currents are flowing in the same direction, the fields will be in the same direction. And because of this, if you click one more time, you'll notice that we get an attractive force. So if the current is flowing in the same direction, which then in turn means the magnetic field is flowing the same direction, this creates an attractive force. And I'll show you further down why this is. But because we're dealing with alternating current, you'll see we'll move over into the next portion, which is at the bottom. The current on the right-hand side switches phases, and when it switches phases, the currents are then in opposite directions. So you'll notice that magnetic fields changed. And because of this, if you click one more time, you will see that it creates a repulsive force. Then the conductor on the left-hand side switches its phase as well, and we go back to the point where we are again currents flowing in the same direction, magnetic fields are in the same direction. It creates an attractive force. And then if we go to the last phase, you'll notice that the one on the right again switched, and now we're back to repulsive force. And this goes throughout the alternating current, and that's what we have in our three-phase system. It's an alternating current. And the conductors, each conductor in the bus bar goes through these phases. And because there are three phases, they're usually out of sync by 120 degrees. So that's it's a sine curve, so 120 degree change between each phase. And as the sine curves move, at times they are at the exact same direction, and that's when you get your attraction. And at times on the sine curve, they will be in direct opposite directions, and that's when you get the repulsive force. Okay, so if we move on to the next slide, we'll zoom in a bit. And what happens is you'll notice as current increases, the magnetic field increases. Okay, and as the magnetic fields increase between the two, your force of attraction starts becoming bigger. And on the right-hand side, you'll see that at a point that the two magnetic fields actually merge with each other. And this is at the worst, where these two conductors will pull to each other. And that's the force we're now trying to mitigate for or design for in our structure. If we move on to the next slide, we'll go now deeper into looking at those two forces I mentioned to you earlier, the line to line and the three-phase fault, or line to line to line. It's easier to say three-phase. So when a short circuit occurs, what happens is the fault generates very strong electromagnetic fields, and we discussed that in those slides before around the conductor. So if there are only two conductors that undergo this fault, which is the line to line, you'll see on the left that picture, those two conductors will then tend to pull towards each other when they are when current is going in the same direction. So the magnetic field is in the same direction. And if they're opposing directions and the magnetic fields are opposing, then they will repel and push away from each other. So that dotted arc that you see there is the basic shape of the conductor moving during this pull and push of the conductors. Now, if you look at a three-phase fault, the one on the right, all three phases are going through this, and usually the outer phases will be in the same direction and the inner phase will change direction. But when they are in the same direction and they're attracting, the phase on the left, let's call that the blue phase. In the middle, we'll call that the yellow or white phase, and on the right, we'll call that the red phase. So the blue and white phase, when they're pulling towards each other, attracting each other, then the red phase on the other side might be attracting it as well, which causes a much smaller movement in the conductor. And when they are repelling, again, the same thing. If the blue is repelling the white, the red is also repelling the white, and that will be causing a much less or much smaller deviation or displacement. And at the same time, the blue and the red, the outer phases, will also repel or attract each other, and that reduces its movement due to the force created from the middle phase. And that's why the three-phase is less of an issue. The displacements and the force becomes much smaller. They cancel each other out, and Azhar will go into a bit of detail into that a bit later. But this brings me to the end of my presentation as we go on to the last slide, which are the force components created due to this electromagnetic field. So now you know that the conductors either attract each other or they repel away from each other. And these create effects or forces on the gantry through the conductor. And we call these forces short circuit forces. And these short circuit forces can be broken into various components, three of the most appealing or most effect. Three of them cause the most effect on our structure, and that's the tensile force. And this tensile force acts along the length of the conductor, which, as you know, the conductor, because it's spanning between two gantries, already has a tensile force. So that increases the tensile force. You get a drop force. As the conductor swings, it falls down. So it's a vertical downward force due to the weight of the conductor as it drops after the fault. And a pinch force, and this usually, Azhar will go into it into more detail, but this is when you have more than one conductor per phase. So they actually try and, because they are pushing electricity in the same direction all the time, they try to attract, and this causes a pinch force, and it's a more horizontal force which compresses the conductor. And these forces and the magnitudes of these forces are calculated, and it changes by the magnitude of the fault current and also the type of conductor used, the bundle in which the conductor is placed. And I hope you got the gist of the discussion on how these short circuit forces are created, from where they are created, and hopefully Azhar can then tie it to the structure that we're going to be discussing as we go along. Thank you for listening to me. Azhar, back to you.
Thanks, Bilal. I'm going to now move straight on to short circuit force calculations. So we get short circuit force calculations and electromagnetic force calculations. You can use either depending on the approach you want to take. But it's basically the force that you going to apply in your structural analysis model that you basically calculating. Before I move on to the actual calculation, just something to understand is the actual movement of the conductor in space due to this attraction and repulsion. So when your electromagnetic force occurs, we have very large movements of flexible conductors. So Bilal mentioned, he touched on it, flexible conductors versus rigid conductors. Rigid conductors are usually not a problem. They're just going to vibrate about its static position. Flexible conductors, on the other hand, you can see from this graph, at 0, 0 is where the conductor is in a static position. And when under your electromagnetic force, we have very large displacements of the conductor, reaching up to 1.5 meters. Delta 1 is usually when the current is interrupted. The conductor has swung out to delta 1, and delta M would be the angle it's at before it drops down. So you can see you have, and this was done in an experiment with a camera, and it measured the tension in the conductor. Now, what's important here is that you can see initially the tension in the conductor was around about 6.5 kilonewtons, and due to the short circuit current and resulting electromagnetic fields, it shot up to 30 kilonewtons in very quick time. So this is a very complex phenomena, and it's a dynamic force or impulse force that will need to be applied onto the structure. In terms of the loading, it would be considered as an accidental load. So continuing a little bit more about the behavior, as Bilal was mentioning, when we have two subconductors that are quite close to each other, are they going to effectively clash due to the electromagnetic forces? And this is called a pinch force, designated as 1 on the graph here. When what happens is the conductor swings out, it comes to location 2, and that's where we have the swing out force. And that's another peak on this graph. The conductor again goes through this oscillation or through this circular trajectory, and it eventually comes to location 3, which is called the drop force, and that's another peak on your graph. So the calculations calculate the magnitudes of these 3 forces. So the calculation that you can use will be done according to the International Electromechanical Commission code. It's interesting, there is no structural engineering design code that provides guidance on the calculation of these these particular forces. So you effectively need to go to a code that is used by electrical engineers. The biggest challenge is the major disconnect between the electrical engineering component and the structural engineering component. So there is a major gap that we actually have, and it needs to be addressed because there is this major disconnect. So that IEC code, the method that they use there, requires an understanding of different branches of physics, like structural mechanics, dynamics, as well as electric currents and magnetic fields. So, so the electrical engineer needs to understand all of these, or the structural engineer needs to understand all of these when doing these calculations. Typically, the electrical engineer is going to provide a value to the structural engineer as to what force needs to be applied to the structure. This must be used with caution, and I'll go into this in the next slide, the reason why we need to be careful when we use this. But essentially, it boils down to the fact that there is a disconnect between the electrical and the structural engineering aspects within this calculation. My opinion is the structural engineer should perform the calculations. At Eskom, the structural engineers have been performing these calculations in recent times, and I think it just works better in that way. So the calculation done according to the code, it calculates your swing out force, it calculates your drop force, it calculates the period of conductor oscillation, and it calculates the angles that I've mentioned previously. Now, as Bilal has mentioned, you get a three-phase short circuit and you get a line-to-line short circuit. A three-phase short circuit would result in higher current, but the resulting short circuit force would be greater in a line-to-line short circuit because some of the components of attraction and repulsion cancel out in a three-phase short circuit. So usually the line-to-line short circuit is going to result in the greater tension in the conductor. Now, one of the biggest problems about the calculation done in this code is that it calculates instantaneous peaks. So it will calculate the magnitude of the force at 1, at 2, and at 3, which is your pinch, swing out, and drop force. However, it does not consider any dynamics of the system. So it does not consider the effect of the dynamic force. It does not consider the effect of the vibrational characteristics of the structure. And this is a major issue and a major gap in this particular code. And so if an electrical engineer is doing it and giving you the magnitude of the force, know that this has not been considered because electrical engineer without knowledge of structural dynamics is not going to know that there needs to be an equivalent static load factor. So there is some guidance on this as well. It's not included in the design code though. It's included in a CEng brochure 205. Effectively, CEng, if I can call it this, it is the AIStructE for electrical engineers in simple terms. So they have a brochure and they have this particular curve, a synthetic curve that they've developed. And I think the first thing that stands out is the large variation in results. It doesn't really conform to our characteristic load concept that we use as structural engineers. So even using this, you need to be careful. Another thing is that this particular curve takes the first vibrational mode shape only, right? And obviously you could have more than one vibrational mode shape that is, it is important, but it still might be valid because it is a synthetic curve. So I think this also needs to be used with care. And again, it just reveals the importance of trying to get something within structural engineering codes. Another thing is that this particular calculation requires the stiffness of the supporting structure. The stiffness, there are a range of stiffness values that are found in the design code. So if an electrical engineer is going to use it, he might use either range, either extents of the range, but again, you're going to have either an over design or an under design. So what I'd say is very important that whichever stakeholder is involved in this, they understand it completely, or both electrical and structural engineers need to look at this code and do this calculation together. So the second approach to determine the electromagnetic force is a direct transient calculation. Effectively, what this involves is calculating your current according to this equation. This equation is found in literature. It's taken, in this case, from the Segre document. When you do this calculation, you'll get a current with time that would look like this. And you take that current and you substitute it into equations that calculate your electromagnetic force, and you get another graph which is shown here. Now, this is your electromagnetic force that is applied perpendicular to the conductor. It's your force of attraction and repulsion between your conductors. So it's applied along the length as kilonewtons per meter. Now, if you do this, what you can do then is model your conductor what supports at the end. You can put pin supports and actually apply the force, the dynamic force is this force on the conductor, and calculate the reaction at the supports, at the pin supports, and that reaction would then be applied to your gantry structure. What's important in this case is that it will work well for rigid bus bars, because in rigid bus bar vibration, you're going to get small displacements. As you can see, for flexible bus bars, we're going to have a problem because of the very large displacements. We're going to have large strains as well, so you need to incorporate geometric nonlinearity. Also important is this method does not consider the transient and spatial changes in magnetic fields. And that is important for flexible conductors, as these conductors undergo very large displacements. Their magnetic fields are also changing in space. And a final method that you can use is the electromagnetic FEA to structural mechanics FEA. Essentially, what this what this entails is a coupled physics problem. There are some software that can do it, notably ENSYS and ADINA. So you can do it using this method, and you're going to get the most accurate results. This has been done in a Segre document as well. And in the document, they did a comparison between the calculation method from the code and the FEA method. And you can see for the swing out force, which is during short circuit, the FEA method produces a higher value than the simplified method. And for the drop down force, which is after short circuit, the simplified method produces a very high force. This was also compared to experimental data, and the FEA method is agreeing quite well with experimental data. So if you are really needing to get a precise value, and I'll go through why that may be necessary now, you may want to use the FEA method. And in this case, I think most of us don't know how to do electromagnetic FEA. We'll either have to learn it, or we'll need to find an electrical engineer that can assist us. The key thing about this is that it accounts for all of the effects, including the changes in magnetic fields in time and space. It accounts for your structural nonlinearities as well as your dynamic effects directly. So I'm going to move on to squeezing out structural capacity. So the relevance of this is that, remember that these substations are located on a transmission network, and the last thing you want is to disrupt the flow of current in certain portions and have unnecessary outages. So you want to prevent as much as possible any retrofits, any extensive retrofits to the structures, because in that case, you're going to have certain outages. So you want to, first of all, try to squeeze out as much capacity as possible. I'll just quickly go through some of that. So you can see this is a typical gantry structure that we use. There'll be 3 phases where the conductors will be located 6 meters apart. The conductor would be attached to this particular box that is fitted within the beam of a structure. So the conductor would be attached to this box. So this box is basically basically plated elements, or it can be channel sections with the web that's in this place, and then you have your flanges on the inside. So just a little bit about trying to squeeze out capacity from the use of design codes. These lattice structures have a lot of angle sections. So those angle sections would have elements that would undergo compression. Using alternative design codes can be a good route to go. This particular graph was extracted from a SciC journal that was done by Prof. Richard Walls and C. Falun. As you can see, the Eurocode has a curve for different types of sections. So we're using angle sections, so we're looking at the red curve. The CEng's document uses a single curve to account for all sections. So this is a nice way to actually try to find a way to squeeze out that additional capacity. If you use your red curve, you're going to get more capacity out. Very important is that the CEng's reliability levels must be maintained. So you need to still ensure that you're using the right factors applicable to the South African environment. I encourage you to read this paper as well. It does indicate that you need to take account of the South African environment, use correct partial factors, use correct limit state factors. Another method is buckling length calculations. Often when we have some sort of rotational restraint, we may not know what buckling length to consider. The Eurocode again does provide additional design codes where you can determine more accurate buckling lengths. You can use EN 1993-31 to calculate your buckling length. So you might get a more accurate buckling length, and you don't need to be too conservative, and you can then squeeze out additional capacity. The next option is taking advantage of ductility. This is provided in the CEng's code under accidental loading. I think it's part 1 of the loading code. They explicitly mention that you can design structural members to have sufficient ductility capable of absorbing significant strain energy without rupture. So you can do this calculation. You can either do it using, again, Eurocodes part 5, 6, or 7. There are closed form calculations in part 5 and 7. Part 6, you'll do more FEA based. Part 5 does have a little bit of FEA guidance in the appendix as well. So, our basic problem in the structure, apart from the buckling of compression elements, is at the location where your conductor is attached. As load is applied, the area around where the conductor is attached will start yielding, and with time, this yielding can result of pull out of the conductor, which is something we want to prevent. So what we do is that we can allow for some yielding in that location. So you can do a nonlinear finite element analysis. Like I said, there are closed form calculations, but those closed form calculations has restrictions placed on them, and in this case, we could not perform those calculations. So we do a nonlinear analysis. Bilinear stress strain curve is fine, as you can see here. In this particular case, the von Mises stress at a load factor of 1 indicated yield stress. Yeah, you're above yield stress, I think around about 390 megapascals. So you can see in this case, we have a very large area of the box that this has already yielded, but it's still fine. It can be used even though a large area will be yielded. And you get this guidance from calculating the plastic strain. You can calculate your plastic strain values and compare it with design codes. Design codes that you can use are the DNV design codes, or you can also use Eurocode as well. What's important to note is that because the conductor is not perpendicularly, directly normal or perpendicular to the face of the box, it's at an angle. You have 2 components, and one of the components is going to push down on this box section, causing compression at the bottom. If the box section has enough imperfections, and if the box section is too slender, you could have buckling as well. And your buckling coupled with your material nonlinearities could cooperate together to cause failure a lot sooner than expected. So I say this because you then need to at least check if geometric nonlinearities will become a problem. You can do this by performing a linear bifurcation analysis. If your critical load factor is very high, you don't need to worry about it. If it's low, I'd say lower than 15, then you need to consider doing a geometric nonlinearity. The reason why I'm saying that lower than 15 is because remember the linear bifurcation analysis does not account for imperfections in for the displaced shape of the structure. So I think that's it from our side.